Hello everyone, my name is Marijn Blommaert and I'm a PhD student here at Delft University of Technology. And together with my colleagues here in Delft and in collaboration with researchers from the Technical University of Denmark, we wrote a perspective called Insights and Challenges for Applying Bipolar Membranes in Advanced Electrochemical Energy Systems. Today we stand in front of the Applied Science building in Delft, a lovely city in the Netherlands. And I suggest we go take a look inside in the lab. Over the last few years, bipolar membranes have been gaining a lot of attention in energy conversion technologies. While before the main interest was focused on electrodialysis applications, now a wide variety of applications implement a bipolar membrane. The reason why that is that a bipolar membrane consists of two oppositely charged ion exchange layers, a cation and an anion exchange layer, with in between an interfacial layer. This gives the freedom to operate in different conditions. Think of pH, composition, concentration, but also in different configurations. Several electrochemical energy applications have successfully implemented bipolar membranes at the lab scale. But besides electrodialysis, none of the other applications like water electrolysis or CO2 electrolysis, fuel cells, or resource recovery have successfully done that at the industrial scale. And to achieve that, we need to improve the current designs of bipolar membranes. And therefore, we've set 5 components that describe the perfect bipolar membrane. One being highly conductive individual bulk layers. Second, having fast kinetics, either in dissociation or association at the interface layer, depending on the orientation of the membrane. Third, having a high water permeability, and then having a long lifetime under operational current density. And then fifth, last but not least, having low ion crossover across the bipolar membrane. The priority for each membrane characteristic differs per application, as the electrolyte environment changes, as well as the applied current density, which can vary 2 orders of magnitude. Let's look at an example. Water electrolysis, for example, typically operates at a current density above 1 amp per square centimeter. That means that a very high activity, conductivity, and water permeability is required. But because of that high current density, the ion selectivity plays less of a role. This is the opposite for an application like resource recovery, which operates at a lower current density. Here, the selectivity plays a key determining role in the overall performance of the system. And that's why it's important to design bipolar membranes for each application separately. Besides current density as an operational parameter, we should also tune the thickness of the bipolar membrane. Because if we lower the thickness, we're going to improve the conductance of the bulk layers and improve the water permeance towards the interfacial layer. And both are going to enhance the performance of the bipolar membrane. However, if we lower the thickness, we're also going to decrease the selectivity. And so for every application, we need to find the proper threshold. In conclusion, the various electrochemical energy conversion technologies demand an equally varying set of properties of the bipolar membrane. Hence, a dedicated approach to design new bipolar membranes for each application is needed, which will allow to fabricate new bipolar membranes in order to be successfully implemented in industrial applications.